Welcome to the fifth video in the Learn Machine Learning video series. And in today's video, we will be tackling some of the more advanced topics when it comes to learning machine learning. Today, we will be discussing advanced classifiers. These include support vector machines and logistic regression. We're going to start with logistic regression, build the intuition to understand it, then we'll jump into support vector machines, build the intuition once again, and then we'll go over a few practical examples and we will finish the lesson. This is a relatively short video, so I hopefully just sit tight, stay back, and enjoy the video. Let's get started. Let's begin with logistic regression, which is really just a harder technique for classification. What is logistic regression? Logistic regression is a classification algorithm that's used to assign observations to a discrete set of classes. Unlike linear regression, which outputs continuous number values, logistic regression transforms its output using the logistic sigmoid function to return a probability value, which can then be mapped to two or more discrete classes. Let's break that down. So I referenced the word sigmoid function, right? And so the sigmoid function is really just a transformation of output that helps us to return the probability value. And so people confuse logistic regression as being very similar to linear regression, but it's actually quite different because logistic regression gives us a probability value, not a continuous number value. It gives us a probability value. This probability value is then being used to map to either two or more discrete classes. Remember, when I say discrete classes, I mean something very definite, right? Discrete classes are categorical. This falls under classification. So when you think about it in the long term, logistic regression is really just a classification technique that uses a probability value to sort between two or more classes. And that's what the sigmoid function is doing. The sigmoid function provides us the probability value that then helps us to map to one of those discrete classes. And I guess people confuse this with linear regression because the name is logistic regression, right? But the idea is that it's logistic because it makes use of a logistic function like the sigmoid curve, right, which is seen in this slide. And remember, the broad idea here, or the broad intuition behind this, is that logistic regression uses probability values from the sigmoid function to assign observations to a discrete set of classes. So that's what logistic regression is really just doing. Let's move on. So let's talk a little bit more about the sigmoid function. So the sigmoid function is the function that helps us map predicted values to probabilities. Right, so the sigmoid function is that equation, 1 over 1 plus e to the negative z. And this equation basically just denotes the output for a certain probability function, right? Input, output. And what's going on with the sigmoid function is that we're taking our input and we're mapping it to any real value between 0 and 1. And that's really impressive because when you think about it, you're getting a distinct real probability value between 0 and 1. And that we can think about that probability value and determine whether it's a certain class or a certain different class. And at the end of the day, this probability value that's spit out by the sigmoid function, this is not the main thing that we want from logistic regression. This is just one step in the process of logistic regression because in the long run, logistic regression is a classifier, like I said earlier. And with classifiers, we want a discrete output as our final output. And remember, by discrete, I mean categorical. So this isn't really categorical, right? This is just a continuous probability value. So what we want to get out of this is we want to turn this probability value from the sigmoid function into a discrete class-valued output. And I guess we're going to find out how to do that. A decision boundary is how we do that, right? So a decision boundary is really just a threshold, or really a line of separation. That's basically when we select a threshold value or tipping point above which we classify values into class 1 and below which we classify into class 2. This is really important because this is where we basically separate between our different probabilities. Right, so take a look at this graph that I've given on this slide. In this graph, it's a sigmoid function, and then there's a decision boundary at approximately 0.5. This decision boundary is basically saying that any probability value, any p of x, above 0.5, any continuous probability value above 0.5, can be considered a certain discrete class, like cat or dog, for example, cat. Any probability below 0.5, or any p of x probability function value below 0.5, can be mol and vice versa, right, the other class. So what's going on here is that the decision boundary acts like a function that separates between the probabilities and helps us to map to discrete classes, right? Without a decision boundary, logistic regression is useless as a classifier because we don't want a probability output, right? The probability output is useful, but it's only useful to a certain extent because we want that final classification output. We want to know the category, right? If you're predicting cats versus dogs, knowing the probability of an image being a cat or dog is definitely useful information, but it's not ideal because we want to know, can we predict it as either a cat or dog definitively? And a decision boundary allows us to do that because we get a definitive answer for whether our probability is above or below the decision boundary. And for more complex sigmoid curves and more complex functions of interest for logistic regression, the decision boundaries get more complicated, right? It's not just always a simple, pretty horizontal line. And what the broad idea here is that for a decision boundary, it's important because it's basically what's so special about logistic regression. It helps us define between two different classes. And as you can see on the left side of this slide, you can see that this is the actual functional notation for this decision boundary. So you see that if probability is greater than 0.5, the class is equal to 1. Probability is less than 0.5, class is equal to 0. It's relatively simple mathematics, right? The decision boundary is what divides between the different probabilities and allows us to classify whether a certain probability value, p of x, is a certain class or just a different certain class. So that's what's going on with decision boundaries. Let's talk about the cost function for logistic regression. So for linear regression, the cost function is mean squared error, right? And we cannot use mean squared error in this case because it results in a non-convex function for logistic regression. Why is a non-convex function bad in this scenario? A non-convex function has too many local minima, right? So what's the point of doing a loss minimization on a function with many local minima, right? We want a function with one absolute local minima, one point where we can definitively say, oh, we found the minimal loss point. So for logistic regression, the cost function is instead this time cross-entropy. Why is it cross-entropy? The cross-entropy function is really just, you can think of it as a smooth logarithmic monotonic function, right? It's relatively simple. The slide on the left is taken from Andrew Ng's machine learning slides, and it really well illustrates the idea of the cross-entropy curve. It's a really simple downward sloping logarithmic monotonic function. And as you can see, it's really easy to identify where loss is minimized, right? At the point where it's lowest. And that's really important because there's not that many local minima. There's one absolute minima. And that's why for the case of logistic regression, cost-entropy works is the best cost function in this scenario because it doesn't result in a non-convex function with many local minima. Instead, it gives us one consolidated function with one absolute minima. So on the right, I guess you're probably thinking about this. On this slide, you see some of the actual algebraic notation for these logarithmic functions for cross-entropy. You don't have to know this because this is definitely out of the bounds of this course. But what's going on here is that you're just separating this into two functions, right? You're separating into it if we're deciding on class 1, if y equals 1, if we're deciding on class 2, if y equals 0. And then for both of those, you have separate cost functions, right? And both of them are smooth logarithmic monotonic functions. And so the main intuition I want you to understand here is that we don't use mean squared error. We use cost-entropy because it results in a convex function with only one local or absolute minima. And that's why it's important to use cross-entropy in this case. Let's move on. Let's talk about a practical example of the logistic regression action. So let's just have an example where we're given data on the time spent studying and exam scores, right? And the idea is that we want to predict test scores, pass or fail, based on like these features, right? Like the time studied, the exam scores, the current grade, effort, etc. And what we can do is that we can use logistic regression to create a decision boundary. And so this is what our decision boundary would basically look like in a really simplified scenario. It would be that if the probability of the student doing well is greater than 0.6, they most likely passed, right? We can discretely assess them as having passed. If the probability is less than 0.6, they most likely failed. And then we can assess that as a discrete category of having failed. And so we can model that in that graph that you see below, where we can place a decision boundary at any arbitrary point, as long as it makes sense. And on the left, you see how this equation would be kind of modeled, right, for a linear decision boundary. And the idea is that regardless of what the problem is, you always do the same thing with logistic regression, right? You have your sigmoid function or some kind of sigmoid curve. You denote a certain decision boundary where you separate between the different probabilities, and then you basically just generate data for that problem, and you assess different data points on that decision boundary. And this is what the fundamental part of logistic regression is, right? It really is just the same immutable process across all types of problems. And compared to linear regression, where we're basically outputting a continuous linear numerical value, here we're outputting a probability, which then gets transformed into a certain discrete category based on the decision boundary for that problem. So that's logistic regression, right? Pretty simple to understand. Just you have to So people sometimes feel a little bit phased by the idea of a sigmoid curve and some of the difficulty in understanding the cost function, right? But overall, it's a relatively simple principle if you understand the idea of the decision boundary, how we separate between probabilities, and what's going on with how to create the decision boundary, and how the sigmoid function really works as a scale of outputting probability. Alright, awesome. Let's move on to support vector machines, and let's kind of demystify this supposedly super difficult classifier. So, what are support vector machines? They're an extension of perceptron. What is perceptron? Perceptron is really just a layer of different networks in a machine learning problem. And the definition for a support vector machine can be thought of as this. It's a powerful discriminative classifier that's defined by a separating hyperplane. Let's break down the vocabulary in that sentence. So once again, a support vector machine is a discriminative classifier defined by a separating hyperplane. Let's reformulate that. In other words, we're given some labeled training data, like any supervised learning problem, and the algorithm outputs some optimal hyperplane to categorize new examples. So what is a hyperplane? Take a look at the graph at the below on the bottom of the slide on the left. And you see there's two clusters of data. This is the graph in R2, right? The second dimension, X and Y. And there's two data points in this graph. Two data points, two data clusters in this graph, and there's a line between them. That line between those two data clusters is known as the hyperplane. The hyperplane is the discriminative line that separates clusters or points of data, or data points, right? So the hyperplane is just another word for separating line. When you create a support vector machine, you're basically telling a classifier to, oh, hey classifier, make a line that divides between some clusters of data. And this is what the algorithm does. In the end, the algorithm outputs an optimal hyperplane, which categorizes new examples. And by new examples, I mean we have this hyperplane in R2 for that data set. We can plug in a completely new example, and based on the positioning of the hyperplane in that new example, we can basically say whether it falls in this category or this category, right? Or yellow or red. And if you're wondering why it's called a support vector machine, the examples or data points for this algorithm are known as support vectors, right? These are the individual data points. Each example or data point you see in these graphs is known as a support vector, thus the name of the algorithm, support vector machines. And this is possible for multi-dimensional problems as well, right? In two-dimensional space, this hyperplane is a line dividing a plane in two parts, or in each class lay in either side, right? In R3, the third dimension, we have a multi-dimensional hyperplane, a hyperplane that's actually a plane, and this divides between two data clusters in 3 dimensions. And so that's really easy to understand. So the hyperplane is really just a fancy word for a line that is able to help us discriminate between two clusters of data. And that's what a support vector machine is defined by. A support vector machine is defined by its separating hyperplane. And that's why it is a discriminative classifier, because the hyperplane is what the algorithm outputs. And that helps us to discriminate between data clusters and also categorize new examples or new support vectors. So that's where we get the name support vector machines, and that's why the hyperplane is the most crucial part of a support vector machine. So let's break down some more vocabulary in support vector machines. So we already talked about support vectors, right? They're the individual data points, it can be of any dimension, that are involved in a support vector machine, right, in the algorithm. So there's another term known as the margin, right? So in this graph, I think it demonstrates what the concept of margin really well. In graph 1 on the left, you see that margin is basically the size of that hyperplane on both sides, right? It's the length of the hyperplane from each consecutive data point, from the nearest data point. And so a hyperplane with a really small margin is relatively close to both data clusters on both sides. A hyperplane with a large margin has really far distance from both data clusters on both sides. And that's important to know because now you can talk about hyperplane having small or large margin. And when we get to how to tune support vector machines and understanding hyperplanes in more complex dimensions, margin is a really important concept because margin really is what we think about when we think of minimizing loss for our support vector machine. So understanding the concept of small margin being very close to the data point clusters and large margin being very far from the data point clusters is huge to understand. And once again, just to reiterate from the last slide, support vectors are really just those individual data points that fall in the tumultuous space of the model, right? Let's move on. Let's talk about something that seems really complex, right? But I'm going to break this down and make it really easy for you to understand. So if you take a course in linear algebra or any kind of matrix-based or vector-based class, then you probably have heard of transformations for vectors or matrices, right? A matrix, in essence, is a transformation of some dimensional space, right? And so let's talk about this problem. So in the topmost graph, the graph in the top left, my top left corner, you see two clusters of data points. You have the blue data points on the outside that forms a separate circle, and you have the red or black data points that form a smaller circle on the inside. And the question is, can you draw a separating line in this plane? This is a very interesting question because, as I said earlier, these data clusters are made to be circular data clusters. So when you think about how to draw a separating line, you can't really draw a separating line because these are circular data clusters, and you can't really draw a line to describe something that's in a circular formation, right? So that's not possible. So we apply something known as a kernel transformation to this data. The graph right below that, the y versus z graph, we've transformed this data to represent it in a different dimensional space. This is a plot of the zy axis, and now we can actually make a separation, which is really cool. And there we go, we made a really nice separating hyperplane line. And that's awesome. So that process of going from that circular clustered graph to changing the dimensions of the graph, right, changing the size, the dimensionality of the graph, is known as a kernel transformation. And it's really important to understand these because, especially in the next video when we talk about principal component analysis and dimensionality reduction, kernel transformations are a huge part of machine learning, and SVMs are essential to have support vector machines. It's essential to have these kernel transformations, right? Because in these kernel transformations, we're basically transforming a line in the original plane and we're mapping it to some more difficult environment, right? So to make that easier to understand, we have a really complex circular data environment in the first graph. And after we transform it with the kernel transformation, we basically transform it into a dimension or a set of dimensions where it's easier to visualize and easier to draw a separating hyperplane. And that's the essence of kernel transformations. We're basically taking something difficult to divide, to make it something that's easy to divide. And then we can also actually visualize this as a circle, right? If you go back to the original xy plane, you could technically draw a separating hyperplane in the form of a circle, right? But that's definitely more complex, right? And the idea is that when you implement support vector machines in Python with scikit-learn, you don't have to actually guess or derive the transformation every time for your data set, right? And typically transformations will be much harder than these ones. And the idea is that the scikit-learn library for Python, SVMs, implementation provides it inbuilt, right? You don't ever have to guess or derive the transformation. And kernel transformations are super useful, right? Because as you can see, with a little algebraic dimensional manipulation, we're able to reduce this problem to a much more easier scenario. And that's why kernel transformation is super important across all machine learning, not just support vector machines. And let's move on. So I talked about the cost function for logistic regression. Let's break it down for support vector machines. In the support vector machine algorithm, we're looking to maximize the margin between the data points in the hyperplane. In this case, the loss function is known as the function of hinge loss. You don't really have to understand the mathematics behind this because this is definitely out of the content covered in this lecture series. But the idea is that you're not going to use the same loss function that you use for logistic regression or linear regression, and it's a completely different maximization problem. Instead of trying to maximize the accuracy of the model in terms of reducing the loss function, you're trying to maximize the accuracy in terms of maximizing the margin between the data points in the hyperplane. So that's the broad thing I want you to understand on this slide. It's that for the cost function in an SVM algorithm, or from where we're trying to reduce the loss, to reduce the loss in an support vector machine, we're basically looking to maximize the margin between the data points in hyperplane. So think about that. A bigger margin is better in terms of minimizing our cost or loss, right? And the actual loss function is known as the hinge loss function. And I'm not going to explain the mathematics right now because it's definitely difficult to understand. So you can look into that yourself. And I guess we'll continue. Let's talk about tuning of support vector machines as one of the last topics for today. When we tune a support vector machine, there's a parameter known as the gamma. The gamma is an important parameter because it defines how far the influence of a single training example reaches. There's high gamma support vector machines, and there's low gamma support vector machines. Let's take a look at the high gamma support vector machine example. In a high gamma support vector machine, only nearby points are considered. And that comes back to the original definition, right? The gamma parameter defines how far the influence of a single training example reaches. So that means that in a high gamma example, only nearby points will be considered, right? Because we're giving very little influence to the single training example, right? So we're only considering nearby points. So if we had some crazy outlier, that wouldn't be considered at all. So we'd have very high gamma, and that wouldn't affect the influence of the nearby training examples. So what I'm trying to tell you is this. The higher the gamma, the more local we stay in our support vector machine. Or in other words, the more nearby points we consider when we're high gamma. When we're low gamma, we also consider far away points that may not be as easy to describe for a support vector machine, right? And the far away points could be like outliers. They could be really distant. They could be pretty decently far from the hyperplane. So it's important to understand high gamma versus low gamma. And for tuning purposes, this is one of the parameters that we adjust in our support vector machine when we try to maximize the hyperplane, right, to reduce loss. And so it's really important to understand that gamma is a really important hyperparameter that we adjust constantly in our tuning of the model. Another tuning parameter is regularization parameter, or C, defined as C. This is a parameter that tells the support vector machine optimization how much you want to avoid misclassifying each training example. Let's break that down. Let's take a look at those two graphs. On the left, we have a low regularization value graph, and on the right, we have a high regularization value graph. On the left, you basically see a graph with a really simple line, right? It's basically just drawing one training line, one hyperplane, and it's being very broad, right? It's just basically saying, let's divide this as best as we can without complicating our hyperplane too much, right? And it actually make some oopsies, right? You can see that there's two data points that fall on the wrong side of the hyperplane, right? The two black circles. That's bad, right? But sometimes that's not a bad thing necessarily for the accuracy of our model, because sometimes you may want to prioritize overall accuracy of the support vector machine over the misclassification of a few training examples, right? Like the two black points. And then you have a high regularization graph on the right. This time, we have a much more different support vector machine hyperplane. This is a much more complicated support vector machine hyperplane, because in this case, we're actually making a bunch of twists and turns, right? And this is actually nice in the sense that we're actually classifying all of our examples correctly, but this comes at the cost of a very different hyperplane, a very much more difficult to optimize hyperplane. Because think about it, going back to when we talk about the cost function for support vector machines, it all comes down to maximizing the margin between data points in the hyperplane. In this case, with very small, very large high regularization value, it's actually very difficult to maximize the size of the hyperplane, which is a bad thing, right? So remember, it's a trade-off. This is all a trade-off, right? You're trying to basically get that. It's a trade-off between the overall accuracy of the model, of the support vector machine, and whether you're misclassifying a few data points or support vector examples, right? So remember, machine learning, hyperparameter tuning is always a trade-off, right? Going back to when we talked about linear regression with the learning rate, right? If you increase your learning rate by a lot, you get there faster, right? You prioritize speed, but you have the issue of that you might overshoot your lower loss minimum point on the parabola of loss, right? Which is bad. But if you have a really small learning rate, you're definitely going to hit the point exactly where you want it, right? You're definitely going to hit the loss minimum, but it just takes forever. So remember, it's always about finding that hidden perfect balance where you get the best of both sides in the trade-off. And that's what tuning is all about, right? And I guess for regularization, it's the same thing, right? Do you want that perfect, completely accurate model, but with a really bad hyperplane with high loss? Or do you want a broad hyperplane that actually has higher accuracy overall, but it does misclassify a few examples? So it's really just a push and pull and an overall trade-off. And when you tune the model, you have to try to balance those two interests very carefully. So that's it for today, but let's conclude the lecture. The takeaways for today's lecture is that we talked about logistic regression versus linear regression, the idea of a decision boundary, the sigmoid function, etc. We talked about the cost function for both logistic and SVM. And for logistic regression, we talked about how the cost function is cross-entropy, right? Instead of linear regression's mean squared error. And then for support vector machine, our cost function is hinge loss. And so for support vector machines, we talked about margin, support vectors, kernel transforms, how to tune them with the gamma and regularization, etc. And I just hope that today's video is really helpful and for you to understand these more advanced classifiers, right? Because we talked about really simple classifiers like a decision tree last time, but today's examples were much more heavyweight classifiers, right? Ones that are used in academia and industry much more often. And these classifiers are not as easy to understand. So I hope that today's video was helpful for you guys to help understand these classifiers by breaking it down, the vocabulary, class functions, etc. And that's it for today. So thank you guys for watching. Today's video was a bit shorter. It was a good video though. Hopefully you guys enjoyed it. Make sure to drop a like on the video and hit subscribe. And I will see you next time. Thank you guys for watching. Next video we will cover dimensionality reduction and techniques for PCA. Thank you guys for watching. I'll see you next time. Goodbye.